Welcome back. This is Tutor Wizard. Please subscribe right here. Hit the notification bell. We're doing linear algebra. This is Alice. Everybody wants to see. Okay, let's just take a pause. Timeout. Kitty timeout. Cat math is my favorite kind. You make 6 kitties. Alice is the newest member with her brother, Ringo. All right, today we're doing linear algebra 1. Chapter 2 is matrices. Section 2.5 is inverse matrix formula. Specifically, what we're going to do today is last time in this section, what we did was derive a way of finding the formula for the inverse matrix. Now we're going to use it to actually force for the trees. Now that we learned how to become lumberjacks and cut down trees, I was like, yay, that wasn't the point. The point was to become architects. Today is finally when we become architects, and we're going to solve linear systems with the machinery and the logs that we had created from the previous video. You're making it hard. What are you doing? You're going to do that? All right, we'll see how long I can do that. Example 1, solve the linear 2x2 system of equations ax equals b using the inverse matrix. So again, there are previous videos where we've discussed this. I know, try to focus on me, not the kitty. And you're just going to watch the kitty. This video is useless. It's moot at this stage. What we're going to do is we view a linear 2x2 system, and where is the system? I haven't written it down because kitty interrupted me. So let me cheat a second. 1, 2, 3, 1. So I've cooked this up. You have x1 plus 2x2 3x1 plus x2 equals, I don't care, 1 equals -2. There. Solve this, and what we're going to do is, I'm trying to give you the hint in the question, which won't happen in general, but we're going to view this system like this, and then we're going to algebraically find the inverse, and then we're going to multiply both sides of this and solve for x. This is the idea, just by, like with the 1-by-1 linear system. I make sure the inverse exists, I multiply both sides, and I solve for x, which will be a inverse b specifically. In ours, what do we have? We have that this is 1, 2, 3, 1 times x1, x2 equals 1, -2. That's the idea. Oh, here comes the other one. What are we going to do with that? From this now, this is 2x2. What I now need is, this is ax equals b. This is what they're saying here. This is a 2x2 matrix. This is a 2x1 matrix, and the outcome will be the same size, which will be 2x1. Oh, magic. What we're now going to do is find the inverse of this and multiply this equation by that inverse. So what is a minus 1? Well, a is 1, 2, 3, 1. So the inverse is 1 over the determinant, which is 1 minus 6, which is -5, times, we have this clever formula, flip those. You want to see me do it again? And then we put negatives on the off diagonals. Remember, this is technically also, I'm going to use this one though, but there's more than one avatar of this also. This one is scalar multiplication. That means it goes onto each coordinate. This is -1/5, 2/5, 3/5, -1/5. I point that out because if you do that and you get the nice, now I have one matrix which is the inverse, you can check by multiplying this by this, you should get the identity matrix. But I'm not going to multiply both sides of the equation by this in this form. I'm going to do this, so then when I multiply these two matrices, or when I multiply this guy essentially by this, I'll do the fractions at the end, was the point of that. So do it in this form. You have more than one avatar of many of your objects at some point. Sometimes it's useful to use this one, sometimes it's useful to use this one. You want to keep both in mind. Now what do I do with this guy? Now algebraically, I'm lazy, I don't actually want to do this. What this says is a times a inverse is the identity matrix. That's what we know. And we know that I2 times x, a 2x1 matrix, is going to be that 2x1 matrix left alone. Oh, you want in? He's giving the sad look. Using this algebra, I'm going to algebraically solve this equation now. I have ax equals b. Oh, this is going to see how long we can last. Get under my butt. And then we're going to multiply both sides by a inverse. That's going to give me a inverse a times x equals b. This is identity. This is going to equal, let's put it here. This is I2 times x equals b. Oh, I forgot it. When you got holding several cats, it's harder to do. Now, what am I going to do? In my last step, I'm going to solve for x, and the unique solution will be a inverse b, matrix multiplication. That algebraic is what we're going to do every time, so if you want, don't do those steps. You know your unique solution will be x equals a inverse b. What does that mean for us? Oh, you want to try and get that? Now I just erased it because I need it. What that says is our unique solution, x, which is x1, x2, is going to equal A inverse, which was negative 1 over 5, 1, 1, negative 2, negative 3, times b, which is 1, negative 2. And this is why I left that on the outside. First do the integers and then multiply on the inside. This is 2 by 2. This is 2 by 1. The inside indices match. My use multiplication is well defined, and the outcome will be 2 by 1. What is it? It'll be 1 times 1, which is 1, plus negative 2 times negative 2, which is 5. Sorry, we have the negative 1/5 on the outside still. And then this one is going to be what? Negative 3 and negative 2 is going to give me negative 5. This is going to give me what? Distribute that in, I'm going to get negative 1 and 1. This is the unique solution. You can put them in there and check. If I put those in there, what do I get? Negative 1 plus 2 times 1 is 1. Check. And then what is the other ones? If I have 3 times negative 1 plus 1, that is negative 2. Check. This is the unique solution. Let's do another one. Ditch these cats. All right, this time what we're going to do is a 3 by 3 system doing the exact same thing with a couple less cats. What are we doing? I need the coefficient matrix, then I have to find the inverse of the coefficient matrix, then I'm going to multiply the inverse of the coefficient matrix by this vector b, and that will give us the unique solution x1, x2, x3. If the inverse exists. How do you tell if an inverse exists? It should be Pavlovian at this stage, if and only if the determinant is non-zero. If and only if the determinant is non-zero. What am I going to do? I'm going to compute a bunch of cofactors, 3 of them specifically, compute the determinant. If that's not 0, I can use this method. If not, what do I do? Hands to the air again? No, well, possibly. But as I do that and I think about what's going to happen is, Chapter 1, we systematically did this. We have Gaussian Jordan elimination to reduce row echelon form, or Gaussian elimination to row echelon form, which will always tell you whether you have one solution, no solution, or infinitely many solutions. If you happen to have the determinant as non-zero, therefore the inverse exists, you will have a unique solution. That's what Kramer's rule says and a bunch of these other things. We'll do more Kramer's rule in the next video too. For now, let's do this. What do I need? A is 1, 4, 3, negative 1, negative 2, 0. 2, 2, 3, and just in case, B is 12, negative 12, 8. The other guy I need. We're going to have to erase this time because there's going to be a whole lot more work. 2 by 2 are always nice, and that's why you do this as the first example, but these are going to get bigger and bigger. Think of a 4 by 4 or a 5 by 5 or a 6 by 6 or, oh my goodness. Using the internet, you're going to use 5 billion by 5 billion. Try to find the inverse of that. Good luck. Supercomputers. What am I going to do with A now? I'm going to find the inverse of it. How do I do that? First, I want to know if the inverse exists, so I'm going to compute the determinant. I'm going to cofactor expand along the top row. So let's compute C11, C12, and C13. C11 is equal to negative 1 to the 1 plus 1, M11, which is equal to M11, which is a 2 by 2 determinant. C12 is negative 1 to the 1 plus 2, M12, which is negative M12, which is negative a 2 by 2 determinant. And C13 associated to A13 is negative 1 to the 1 plus 3, M13, which is equal to M13, which is some 2 by 2 determinant obtained by blocking off rows and columns. Now I switch gears. This is going to tell me I block off. In this one, I'm always going to do the same, but we need to use it later. So I'm going to block off row 1 and column 1. That's going to give me negative 2, 0, 2, 3, which is equal to negative 6 minus 0. And the next one, M12, is obtained by, first of all, this is going to equal negative times, don't forget the negative. I'm going to block off row 1 and column 2 this time, so I'm going to get negative 1, 0, 2, 3, which is going to give me negative, negative 3, which is 3. Then for M13, I'm going to block off row 1 and column 3, which is going to give me negative 1, negative 2, 2, 2, which is going to give me negative 2 plus 4, which is 2. Now I have those first 3 cofactors. Let's keep track of those guys. What am I going to do with those? Erase and compute the determinant. Therefore, the determinant of A is equal to A11 C11 plus A12 C12 plus A13 C13 by our theorem. This is cofactor expansion along row 1 of A. A11 is 1, A12 is 4, A13 is 3. C11 is negative 6, C12 is 3, and C13 is 2. Put those in there, stir the pot, we get soup. Determinant soup. This is going to be negative 6 times 1 plus 4 times 3, 3 times 2, which is 12, which is not 0. Because the determinant is non-zero, we know the inverse exists and we can compute it. How am I going to do that? Since I've already computed 3 cofactors, I might as well compute the other 6 and use this. The cofactor matrix transposed times 1 over the determinant will be the inverse. All right, to recap, this is the original matrix A, which was the coefficient matrix of that 3 by 3 linear system. Then what we did was we found the 12 or the 9 cofactors. We create the cofactor matrix. Then we transpose it. Then the inverse of a matrix using the multiplicative formula is 1 over the determinant cofactor matrix transposed, called the adjunct matrix or adjoint. Then for us, we had the determinant was 12, so 1 over 12 times this cofactor matrix transposed. I can distribute this into there, and then I get a bunch of fractions. You should try doing this using row reduction and Gaussian elimination, and you will see that this is the same matrix you get, but you're going to have to do a lot of row reduction computations with fractions with the denominator 1/12 possibly. You'll get the same thing. Now, what do I do with this? We finally cut down trees. We don't want to become lumberjacks. We want to be architects. What I'm now going to do is use this to build the unique solution of this linear system, x1, x2, x3. Let's use this and multiply by the original column vector. Okay, putting that together, this was the column vector B for our original 3 by 3 linear system. Then we found the matrix inverse. In this case, we used the formula because that's what the section's called. You can also use Gaussian elimination and put the block identity behind and row reduce. Either way, inverses are unique, so this is what you should have got. Then what do I use that for? The unique solution to the system is therefore x is equal to A inverse B. We now have A inverse and we have B. A is a 3 by 3 matrix. B is a 3 by 1 matrix. The inside indices match. That means the multiplication is well posed. And the size will be the 3 by 1 vector also. I leave myself room because I know I have to do dot products now. Matrix multiplication. Oh, dot product. You haven't seen that yet. Watch chapter 3. You'll learn what dot product is. How do I get the first entry? That will be this row times this one in dot product. So what am I going to get? Negative 12 over this is negative 6 plus 6 plus 4. Cancel, cancel. And then in the next one, I'll simplify in a second. Equals. Do an intermediate step. That's going to give me, now what am I going to get? That's going to give me 3. And then we're going to get plus 3 again. And then in the last one, we're going to get what? Minus 2. In the last one, we're going to get 12 over 6 is 2. Plus negative 12 over 2 is negative 6. And then 6 over 8 is really plus 4 over 3, or 8 over 6. What is that going to give me? 4, 4. In the last coordinate, what do I have? If you can't see it, do a side calculation. I have negative 4 plus 4 over 3. What should I do now? Yeah, this is what's also amusing. I can train you to eventually use the multiplicative formula for an inverse and solve linear 3 by 3 systems, but then I make you add fractions. You're like, I don't remember how. Get a common denominator. This is 4 over 1. I want a common denominator of 3. Multiply it by my... Oh, there's my favorite dirty trick. I multiply by 1, which leaves it alone in regular multiplication for real numbers. Now what's that going to give me? Negative 12 plus 4 over 3, which is going to be 8 over 3. Sorry, negative. So we're going to get a negative 8 over 3. Please subscribe right here, hit the notification bell, and I'll see you next time.